Before I continue on to the next problem, as I mentioned in the last video, when we did this example, the left area came out to be 0.7595. We had the right endpoint area coming out to be 0.7095, and the midpoint area coming out to be 0.6912. Which gave me idea that maybe I typed in the right area or the right endpoint area approximation in the calculator incorrectly, and I checked on it and I did. Okay, so this is how we calculated the right endpoint approximation. This was the right endpoint, 1.25 for the first rectangle, then 1.5 for the second, 1.75 for the third, and 2 for the fourth rectangle. So then I redid it, and I get 0.6345. So 0.6345. There we go. That's more. That's a number we would better expect since the midpoint area was 0.6912. Okay. So, sorry about that mistake. This would be the correction to fix it. Again, I don't know exactly what I typed wrong in my calculator, but I redid it and I got this answer right here. Okay? So, we talked about area now. Let's talk about distance. How is this related to distance? So the distance problem. We know that rate times time equals distance. Okay, rate times time equals distance. Now rate, this is a velocity right here. Okay, something like meters per second. You're multiplying this by some time. Everything's going to be in the same units, seconds, and you get a distance, which these cancel out, and you do get meters. You do, in fact, get a distance. Okay, so how is this related to finding areas? Say that I know the velocity of an object at some time t, okay? Say the velocity looks something like that. I don't know, I just made this curve up, okay? So this is v of t, the velocity. Now say we wanted to know what is the distance traveled here. Let's have it start right there. What is the distance traveled from here would be t is equal to 0 to over here t is just equal to some t value. I'll label this time instead. Time, and over here velocity. So we're just going to some t, okay? Now we saw that the rate or the velocity times the time equals the distance. So let's go ahead and do this. Let's take this interval. Let's go ahead and split it up into equal subintervals. Let's go ahead and make some Riemann sums. That's a really bad straight line. That's equally as bad. Okay, so let's go ahead and let's look at the dimensions that come out of one of these rectangles. Okay, so that's what we're doing. We're gonna split this this velocity up into intervals and make rectangles. Each one are the same. And then if each one are the same, the length down there is delta t, okay? The height at every single one of these rectangles is some velocity, some v of t, okay? I'm just going to call it v of t. And now if I find the area of this rectangle, area is length times width, which length times width, well, v of t times my width, delta t. I no longer need the picture. I got what I need to explain the idea here. I found the area is equal to the velocity times delta t, okay? For every single rectangle, it's some velocity times the distance, the time intervals. Let's look at the units. This is in meters per second. It's a velocity. Delta t, well, that's a time. Delta is just the change in time, so it has units times, so seconds. Cancel, cancel, this equals meters. So the area under the velocity curve is the distance. It's the distance traveled from time equals A to time equals B, okay? In our example, we went from 0 to t, okay? You could do from like t is equal to 5 seconds to t equals 27 seconds, okay? It does not necessarily have to be 0. Does not it has to be a positive number if we're talking about time here. But this will give you the distance traveled, the area underneath the curve, in this case, is synonymous to distance. So the area underneath the velocity curve is the distance traveled from whatever starting time point you want to the ending time point you want, okay? And of course, there will be overestimates and underestimates. This will give you the approximate distance. It depends on how many rectangles you split this your time interval into. Okay, so let's go ahead and look at this example. It's on page 376. It says the speed of a runner increase steadily during the first 3 seconds of her race. Okay, so we know her velocity is increasing. That's all we know. It says her speed at half-second intervals. So we have a radar gun on this person, and it reads every half second. So we know our delta t is 0.5 seconds. So every half second interval, it gives you a speed. Now, in that table, they tell you, it says find the lower and upper estimates for the distance that she traveled during these 3 seconds. So it gives you her velocity over these intervals, okay? Now, what they mean by find the lower and upper estimates for the distances, it means it wants you to find a lower endpoint approximation and find a right endpoint approximation, okay? And once you do that, you'll be able to see which one is the lower estimate, which one is the upper estimate. So our delta t is 0.05 seconds. So when we find, let's do a lower end. Lower endpoint. So the area is equal to delta t, which we know is 0.5 times. Now they give you the function values, okay? We could draw this on a graph. At 0, she's at 0. At 0.5, She's at 6.2, wherever 6.2 is. So like that. So it goes something like this. It's gonna be a choppy graph. Let's see, at 1 second. Let's see, at 1 second, she's at 10.8. So 10.8, way up here, something like that. You can, since these are very nice shapes, triangle, here's a trapezoid, you could find the area of each shape and do it that way. But this is good enough illustration to explain how to get which one is the left endpoint, which one is the right endpoint. Okay. So what we need to do, since we're doing a lower endpoint approximation, we need the velocity of this rectangle, of the first rectangle, at the lower endpoint. So what's really nice about having a table of values is because all you have to do is pick off the numbers from the table and put them there. You don't have to actually find the function values, and using your calculator will be easy because you'll just be typing in the numbers. You'll see in a moment. So if I were to draw a rectangle between these two values, I would use the left endpoint because we're doing a lower, or I said lower end, left endpoint. I meant to say left endpoint, I apologize. So the left endpoint would be this value. Now I need the velocity at this value. Well, the velocity at that value, if I look at the table, is 0. So if you notice, out of the two, I picked the left one, 0 and 1.5. I picked the left t value. Now if I go between 0.5 and 1.0, and I'm looking at the table, I'm going to pick the left endpoint. So I need the velocity from the left endpoint plus 5.2. You do the next one for 1.5. I'm going to pick the velocity for 1. If you notice, out of those two, I'm always picking the one on the left. So this is going to be 10.8. Plus the next one is 14.9. Plus the next one, let's see, 18.1. Plus the next one, 19.4. So 2.0, 2.5, 3.0. So left endpoint out of these two, this is the left one, out of these two, this is the left one, out of these two, this is the left one, out of these two, this is the left one, out of these two, this is the left one. So I end on this one. So I need the velocities from 0 all the way up to 2.5, which are these ones. Now, if you notice, when we do the right endpoint, on the right, this one, on the right, this one. So it makes it a little bit easier for us when we do the calculations. We're just going to get rid of this 0 value. And then we're just going to replace it with the 3, because that's going to be the last right endpoint. Okay? So noticing little patterns like that makes it a little easier, makes the work a little less cumbersome. So now, just plug all these in on the calculator. 0.5 times 5.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4. Close parentheses. 34.2. So the distance that she traveled is 34.2. Let's see, what are these units in? These are in feet. So in the first 3 seconds, she traveled approximately 34.2 feet. Now, let's go ahead and do the right endpoint approximation. So again, if I were to go ahead and make rectangles, and if I were to look at these two, this interval right here, I'm going to pick the one on the right, so I'll make a rectangle like that. Out of these two, I'm going to pick the one on the right, I'm going to make a rectangle like that. And then this one, I pick this one, make a rectangle like this, whatever it goes up to. But if you notice, I'm always picking this one, this one, this one, the ones on the right. So in the table, I don't need this velocity. That was right here. So I could just erase that. Our answer is going to change. And then the one that we added to this sum, if you notice, these middle ones are exactly the same as the previous one. The only ones that change are the endpoints. Okay? So now we pick the velocity from 3.0. This is 20.2. That's all we had to do. We just had to change a single number. So plus 20.2. And we get 44.3. So let's see. The distance was 44.3 feet. So this is what the question was asking us. Over this 3-second interval, find the lower and upper estimates for the distance that she traveled. The distance is related to an area in this case. It's the area underneath the velocity function. Okay? So in this case, we were given a table of values and we were able to construct rectangles and create a Riemann sum out of it. From that Riemann sum, we found that a lower estimate is 34.2 feet, an upper estimate is 44.3 feet. So we can conclude over this 3-second interval, she ran a distance between 34 and 44 feet. Okay? Now, if we had a speed gun that took sample points at, say, 1/4 of a second instead of a 1/2 second interval, our table would be bigger. We'd have double the amount of data points. So then the areas that we calculate are going to be closer to the actual area. And I would expect they would probably shrink a little bit, be a little bit above 34, a little bit below 44. Okay? If we keep making this smaller and smaller, we get closer and closer to the actual area. And that's going to be the theme for the next couple sections on how these areas are related to something called an integral.